Do you know what I think about at 3 in the morning walking through airports? China just turned on an underwater AI data center near Shanghai. Microsoft restarting a nuclear power plant. Elon building a private power station for GPU clusters. Yeah. I thought you would want to know, obviously, about the 5 different ways that we're solving for AI constraints.
Jet lagged. Yes, people. Getting pulled aside by TSA for recording this very content? Also a solid yes. My 3 a.m. thoughts about solving the physical constraints of AI, it affects all of us. That's why I'm sharing it. There are 5 constraints we are facing right now, and the industry is solving for them. They are heat, they are power, they are compute density, they are resource availability, and they are latency. The number one constraint, cooling. The thermodynamics of data centers. The underwater data center off of Shanghai's coast uses the ocean itself as a heat sink. These state-of-the-art AI GPUs consume an enormous amount of power, and nearly all of that power is released as heat. If you have a 100 megawatt AI cluster, it produces roughly 100 megawatts of heat. All of that heat must be removed from the facility on a continual basis. What Shanghai figured out is they close the refrigerant loop. It transfers the heat from the chips into the surrounding seawater. It is replacing the cooling towers that are commonly being used in these large land-based centers. The Shanghai facility's power usage effectiveness is below 1.15, meaning 85% of that facility's energy goes directly towards the computing. To compare and contrast for you, the traditional data centers operate between 1.4 and 1.8 PUE, requiring significantly more energy to cool all of these operating facilities. So Shanghai solves the cooling constraint by using the ocean itself. Number 2 constraint, power availability. And this is where we're talking about energy systems. I coined this the nuclear adjacent data center. Microsoft signed a 20-year agreement with Constellation Energy to restart the 3 Mile Island nuclear plant for its AI workloads. Amazon Web Services, they acquired a 960 megawatt data center campus powered directly by the Susquehanna nuclear plant. A 100 megawatt AI cluster consumes 100 megawatts of energy continuously. Roughly, that's the same power draw as about 80,000 US homes. Nuclear plants operate at more than 95% capacity and can run 18 to 24 months before refueling outages. The power plant adjacent data center solves the power availability constraint and the volume constraint through dedicated base load generation. The number 3 constraint, compute density. This is where we're actually talking about computer engineering. Hyperscale AI factories come into play. xAI's Colossus facility houses more than 500,000 GPUs. The point of this is for frontier scale AI training. An example of this would be a single NVIDIA GPU rack can consume roughly 140 kilowatts of power. And that's about 10 times what a traditional server rack consumes. So to support that particular load, xAI built an adjacent gas-fired power plant. So this particular architecture solves for the compute density constraint by concentrating hundreds of thousands of GPUs into a single facility. 4th constraint, resource availability. We're talking about infrastructure engineering, and this is one of my favorites, floating ocean data centers. So we talked about on the ocean floor, this one is on the surface. We're developing floating data center nodes that generate electricity from wave energy, and of course the surrounding seawater cools it. It solves the resource availability constraint by combining these 4 attributes: power, cooling, compute infrastructure, and a single platform to do it with. That's my favorite. The 5th one is the latency constraint. And this is network engineering. AI cannot always rely on the distance to a centralized data center. So edge data centers place compute inside cities, campuses, cellular networks, so they can reduce the latency under 10 milliseconds. Latency is the time required from a system to send information, receive the response, and then act on it. Centralized centers can require about 50 to 100,000 milliseconds for the data to travel from the center to the network. A self-driving vehicle traveling at 60 miles per hour moves nearly 9 feet during a 100 millisecond delay. These are environments where milliseconds actually matter in regard to safety, performance, financial outcomes. This architecture actually solves the latency constraint by moving compute physically closer to its user. We are becoming an AI native planet. We need to solve smartly physical infrastructure for it.